Today we have another test, the ratio test. And this is, I guess I didn't write my pages down. All right, this is on page 223. So the ratio test is useful, as you can see here. Whenever you're involving factorials or exponentials, just really ugly looking expressions, that's when this is really going to come in handy. There's three kind of things you need to know. First off, okay, it's going to converge. So what we're going to do is we're going to take the limit as n approaches infinity of the nth plus 1 term divided by the nth term. So this, whatever they give us in the problem, is going to be the denominator, and we're going to mess with fractions and keep change flips. So we won't often have too many mixed fractions and fractions kind of thing. And the first term will be the next term. So the numerator is the next term. The denominator is the term in the actual expression. If all of this is less than 1, then this series will converge. Okay? So less than 1, it will converge. If it's greater than 1 or equals infinity, and to me, infinity is greater than 1, so it's really only one thing to remember here, in my opinion, then it diverges. We have an inconclusive situation if it actually equals 1. So if this ends up happening, the ratio test doesn't tell us anything about convergence or divergence. You'll have to use a different test to try to figure that out. So those are the three different cases of the ratio test, and we'll just go through some examples. All right. So in this first example, all right, I've already written it out. So the first example is the series from n equals 0 to infinity, n factorial over 3 to the n. Okay. So what we do is our first, this is really here. This is our a to the a sub n plus 1. So the n plus 1 term. So instead of it being n factorial, it's n plus 1 factorial. Instead of 3 to the n, it's 3 to the n plus 1. And then on the bottom, what I really have is this, n squared divided, n factorial divided by 3 to the n. Well, this really means n plus 1 divided by n factorial 3 to the n. Okay. And so when I keep change flip, I multiply by the reciprocal of this. And so essentially, the way you're going to want to set these problems up is you're always going to multiply by the reciprocal of this, because that's the same as dividing by it, since that is the a sub n term that would normally be on the bottom. And then the first term is just the normal a sub n, but you sub in n plus 1 for all the n's. So that's where you see an n plus 1 here and an n plus 1 here. Okay. Now the trick is to simplify this and then try to figure out the limit. And here's where it gets a little bit tricky. Here's the way I'll show you how to do this. You know, and I'm obviously accustomed to doing this, so this one's going to be a little trickier for you. Okay, so I have 3 to the n on top and 3 to the n plus 1 on the bottom. So you could think about this. I mean, you could use your subtraction rules, but I'm gonna show you something a little bit different. Okay, this means 3 to the n times 3, because n plus 1, same base, add the powers. And what essentially happens then is the n's cancel out. So the 3 to the n's cancel out. So I'm just left with a 3 on the bottom. Okay. And then here, this is really, and we've talked about this before, n plus 1 times n minus 1, etc. This all is n factorial. So the n factorial cancels out, and I'm just left with, I know that's a crappy looking n plus 1. All right, so that's kind of the work. And as you start doing more and more of these, you're going to get a lot better at figuring out how the stuff all cancels. Long story short, this is what I end up with. N plus 1 over 3. And now you have to find, now it's as simplified as we can get it. And usually you want to do that first because then it's easy to find the limit. So as n approaches infinity, this numerator is going to approach infinity, which means the limit of all this is infinity, okay? And so, which I like to say is greater than 1. Based on the rule, I don't think you actually need to say that, but I like to, just because to me then there's only 3 rules I have to worry about. Less than 1, greater than 1, equal to 1. Greater than 1 means that this diverges by the ratio test. And that's kind of all there is to the ratio test. And we're gonna use this a lot moving forward. So it's gonna be good for you to get good at this, okay? So let's work on the next one. Now that I already have an n plus 1 in the top here, to get my nth plus 1 term, I'm gonna have to add another 1 to that. And then so basically I'm gonna flip this, and that'll be my second fraction, right? Divided by this means multiply by the reciprocal. So here's what that one's going to kind of look like. So when I add 1, that becomes n plus 2, add 1 to the top. Now be careful here, make sure you add it inside parentheses. And again, I just flipped this other one. So now see if you can go ahead and cancel and reduce this down, pause it, and see if you can come up with that on your own. So hopefully you've been able to do that. So let's start right here. I've got, I could just subtract the powers to n plus 2 minus the quantity n plus 1. And so that's just going to give me 3 on the top, 3 to the first on the top. So here I've got a 4 to the n plus 1. So it kind of works like this. So this is going to leave me a 4 on the bottom. And I can't cancel anything here. These are not factorial. So this is n squared. This is n plus 1 quantity squared. So that's going to stay the same. So here's where I'm at. Like I said, I've got a 3 on the top, the n squared stays. This gives me a 4 on the bottom, the n plus 1 squared stays. Now when I test the limit, as you know, we can really ignore this plus 1, because as this approaches infinity and this approaches infinity, this is really infinity squared over infinity squared, which is just infinity over infinity. So that basically gives me 1. And so my limit is just 3/4, which of course is less than 1. And therefore, this original series converges by the ratio test. All right, here are 2 more examples, 3 and 4. And this one's messy, and we'll talk about that in a minute. But here's number 3, okay? So we're still going to use the ratio test for this one. Okay, so again, this just gets flipped and is on the bottom. And the thing that's nice about this problem, since we always take the absolute value in the ratio test, this just drops out, because this is, -1, 1, -1, 1. So the absolute value essentially makes this part obsolete. So go ahead and try and set that up. And here's what you should have had. And let's go through this a little bit. So I add the 1 inside to the n. Then when I add 1 to this, I just get n. And of course, when you flip that, that's what you get. All right, so what I really have here is I have n and n to the 1/2. So it's like n to the 3/2, and n to the 1/2. So n to the 3/2 again. So I get 1. Okay, all that gives me 1, which means that this test is inconclusive. The ratio test is inconclusive. So I have to use a different test in order to figure out convergence or divergence. Now, maybe you were thinking right off the bat, why don't we use alternating series test to see if that works? Well, that probably would have been a good idea to check for, at least, because the power on top with n is smaller, the power on top is smaller than the power on the bottom, which leads me to believe the limit of this is going to be 0. So, of course, with the alternating series test, you have to show, 1, that it's alternating, and that it's decreasing, okay? And so we could quickly take a look at decreasing. This is square root of 2, this is 1. This is square root of 3, this is 2. Square root of 4, that's 2, and then that's 3. So it is going down. And so we can just have to state that, 1, that it's alternating, 2, that it's decreasing. Now we need to find the limit of this, and as I alluded to earlier, since the power on the bottom is bigger, this is going to grow faster than this, which means this is going to approach 0. So we meet all the criteria of the alternating series test. So this series is actually converges by the alternating series test. All right, last problem. You're probably wondering about this double factorial. Well, here's what double factorial means. It means the odds or the evens. All right, so normally with factorial, we start at, let's say 9, and we just work our way down 9, 8, 7, 6, 5, 4, etc. When you see a double factorial, you go based off of the first term, and so in this case, 2n plus 1, is that odd or even? Well, the 2n is always even. Adding the 1 makes it an odd, which means this term is always odd. So you're going to take every odd term. So if I started, if for example, I had 9 double factorial, this would be 9 times 7 times 5 times 3 times 1. So you skip all the evens since I started with an odd. Here I start with an odd. And so I do the same thing. I would skip the 2n and I go to 2n minus 1. And as you can see, it's written out over here. They did it for us already. If this was 2n double factorial, then it'd be 2n, 2n minus 2, 2n minus 4, etc. So understand when you see that double factorial, that means just the odds or the evens based off of whatever the first term is going to be. All right. So again, with ratio tests, this is one of those ones, a perfect example of a crappy, factorial looking thing that the ratio test is going to be really helpful for. And so go ahead and try to set that up. And fortunately, since we wrote some of these out, it's going to be helpful, okay? So instead of going to the 2n plus 2, we actually replace n with n plus 1, so that ends up being 2n plus 2. So when you have a factorial like this, what you really want to do for that first term is you're going to replace this n with n plus 1, but in parentheses. Oh, there should be another plus 1 there. Oops. Let's start that one again. Because that n plus 1 is just in place of this n. And then I still have this other plus 1 here, and that's all, right? That's really how we replace this here. And this is 2n plus 2 plus 1, which is plus 3. Or again, you can think about it as going, all right, when we go down, we got to go up to the term before it, which would be 3. Since you have to skip from, you wouldn't go to 2, you'd go to 3, skip over the even one. Anyway, and then 3n plus 1, and then same thing down here. I go to the term right before it, and then this is n plus 1. Of course, this is just flipped. All right, so now we got to get into the messiness of this. Here's my 2n plus 1 double factorial, okay? This is this times 2n plus 3. So basically, this is going to completely cancel out, and then these are going to go away, and I'm going to be left with 2n plus 3. The 3 to the n over 3 to the n plus 1, that leaves me a 3 on the bottom. 2n minus 1, 2n plus 1, I can't do anything with that. And then I have one more term down here than up here, so I'm going to have an n plus 1. So here's what I end up with. This and this cancel. This all completely cancels, but I'm left with the 2n plus 3. The 3 to the n plus 1, that gives me the 3. 2n minus 1 is still here. 2n plus 1 is still here. The n factorial and the n plus 1 factorial cancel to give me n plus 1. And now it's a matter of trying to figure out what this is. And if we look at just the leading coefficients, right? 2n, there's 4n squared. Then I've got 2n and n and a 3, so that's 6n squared. So really what I have here is, in terms of the limit approaching infinity, 4n squared on top, 6n squared on the bottom, all right? That's what we're really looking at. Well, and of course, that's just 1, so this limit approaches 2/3 or 4/6, okay? Which is less than 0. Sorry, less than 1, not 0, less than 1. So therefore, my original series converges by the ratio test. Okay, so this one converges by the ratio test because the limit of this whole thing equals -1. Now we've gotten into a bunch of different tests now, and so let's start talking about how to kind of put them together and try to figure that out. So, the first thing is saying, all right, do the nth term test. That's easy enough. Does the limit as it approaches infinity not equal 0? Okay, then it diverges. You can do that one pretty quickly. Is it a special type? So we've had geometric, we've now talked about p-series or alternating. Okay, so does it meet any of those criteria? And then if so, maybe you can figure that out, right? Geometric is, you can do a test for both convergence and divergence. P-series test, both convergence and divergence. Alternating is only a test for convergence, right? That doesn't test for divergence. You have to use a different test. So you could potentially look at convergence through alternating. Then with the integral test, all right, is it something that can be integrated without a lot of pain? Factorials or exponentials, okay? Can you compare them to another one of these that you already know, right? Direct comparison test. Is the algebra messy? And so that's where you might want to do the limit comparison test. So this is starting to give you an idea of how to approach each of these problems and which test to maybe look at. And this is the analogy I talked about with factoring. When you first learned how to factor, everything was greatest common factor. And then all of a sudden there were difference of squares. And you're like, okay, I got to go down the list. Oh, wait, there's 3 terms. Now a trinomial. Which kind of trinomial? Oh, there's 4 terms. Maybe I got to use grouping. That kind of thing. That's the same idea as going on here. We've come up with this giant list. And actually, we have completed. This is the last new test. And so we have to figure out when to use which test. So this is a kind of a good approach. And then, of course, there's also all these tests. And this is really a breakdown of everything, right? Everything that we've talked about so far. These are all the tests that we're going to have and lots of different things. I definitely, if I were you, would start, if you haven't sort of committed these to memory, really start working on that, because trying to understand when to apply what test in what circumstances and how to use it properly is going to be really important.